All right, continuing our discussion of geometry. As I had stated, the other big shape, right? Triangles and rectangles, without a doubt, all right? Poly those are shapes, polygons that we're most familiar with. But, all right, circles, that might be the most commonly occurring shape and, all right, one of the strongest structural shapes as well, which is why things are always built with columns. So a couple of notes. Radius, R, that is the distance from the center to the edge. The diameter, all right, is the distance all the way across, all right, the circle. The circumference, which is kind of like perimeter, all right, 2 pi r, right? We've already dealt with pi a little bit, all right? That the value pi, all right, is all about uh the special reserve number 3.1415926535897932384, etc. All right. Um, a number strongly associated, all right, with circles, pi. And then the area of a circle is pi r squared. All right. Fun side joke, in case you haven't heard it. A student goes home to their instructor, to his dad, all right, after learning like all about circles and stuff. And he's like, Dad, I'm really, really confused. I don't understand the area of a circle. And the dad says, What's the area of a circle? And the son says, Well, the instructor told me it's pi r squared. The dad thinks about it for a minute. And he goes, I don't know what that college is teaching you. Pi r round, cornbread r squared. See, so now you should never forget, all right, the area of a circle being pi r squared. All right, so let's look at an example applying those equations. A uh, a running track, all right, 5 meters wide, has dimensions as shown in the diagram here. All right, the ends of the track are semicircles with 20-meter diameters. What is the surface area of the track? So we're told, right, we have distances 5 meters, all right, 5 meters. If the track is 5 meters wide, okay, the whole thing is 20 meters. That means the actual radius of the whole thing is 10 meters. But if we know that the distance of the track is 5 meters, that means this inside radius is also 5 meters. Now, with two semicircles, right, if I'm trying to find the area of the track, all right, I have the area of the track, all right, is two half circles plus two rectangles that are the same. So if I have two half circles, that's basically I have a circle. And essentially I have a donut, right? In order to find the area of a donut, that's the area of the big outside circle minus the area of the smaller inside circle. Well, we identified the area of the big outside circle, all right, has radius of 10 meters. The radius of the smaller circle is 5 meters, which means I have pi r squared with 10 minus pi r squared with 5. So if I have, all right, the area of the two semicircles, then I just need the area of the rectangle. Good news, the area of the rectangle, all right, 5 meters by 100 meters, and we have two of those. So the area of the track equals the 235.62 that we found above plus 2 times the area of our 5 times 100. That makes 1,000 since there are two of those. And then so hence our total area of the track, 1,235.62 square meters. So doing areas, all right, pictures, very, very interesting. All right, break it down piece at a time. Another interesting formula we have is the arc measurement formula, and this is really more of a ratio formula, right? 360 degrees, that's the all the way around, okay? If you turn into a full circle, that's what we call 360 degree, right? 360 degree vision. I can see all the way around me. So any fraction of that, of 360 degrees, all right, sets up a ratio. That lines up with the ratio of the length of an arc cut on a circle over the total circumference. Circumference is all the way around, right? That's the perimeter of a circle. So I can set up a ratio of those two concepts. So let's look at an example. At high noon, the sun hits you at a 14.45 degree angle. A friend of yours is 1,000 miles from you. What is the radius of the Earth? So I have this distance, all right? That is the arc cut. And I'm told, all right, the angle, all right, of the person A, right, is 14.45 degrees. Well, using corresponding angles, that gives me the angle 14.45 degrees for the radius, for the angle at the radius of the center of the circle. So I can set up my ratios. 14.45 divided by 360 equals, all right, the arc cut was told to us to be 1,000 miles, equals the total circumference. So I can solve this ratio, all right, cross multiply and solve this down. Then, right, the circumference of a circle is 2 pi r, right, as seen in our equations, all right, previously. So then I can actually solve this to find what is the radius. Divide both sides by 2 pi. And just as a note, careful when you do this in the calculator, all right, your calculator sometimes treats pi kind of differently. So make sure you put this in parentheses in your calculator. And that will give us a radius of 3,965.1 miles. And just be aware, radius of the Earth is about 3,960 miles on average. So that actually is true. One other equation, and this one is more just about kind of like we did with semicircles. If you have a semicircle, well, that's just half a circle. So I could find my equation and multiply it by half. Similarly, I can do that with the measure of an angle divided by 360, right? If I want 1/6 or 1/5 of a circle, I just take that value and I multiply it by 1/5, because the equation of the area of a circle is pi r squared, as we will always remember because of the joke. So I can always just use that fraction and multiply it by pi r squared to find, all right, the area of a fraction of a circle. For example, John's mother makes the best slice of pie in 3 counties. All right, when she is cutting pie for John, he asks for an 80-degree piece, as we all do. All right, if the radius of the pie is 6 inches, what is the area of a slice of pie John got? So if he has an 80-degree, right, divided by 360, pi, we are told the radius is 6 inches. Pi 6 squared, and then we can solve that down. which gives us 25.13 square inches. All right, now advancing to 3 dimensions. All right, well, still doing some 2 dimensions. So in 3 dimensions, okay, we live in a 3 dimensional world, which means everything we're going to talk about is volume. But the other big thing is surface area. So volume, right? That's the area, right? The space the object takes up. But the surface area is just the faces of the object. And while we have equations for a few of these, mostly, all right, remember that the general concept of volume is going to be the base area times the height. That's how you get to volume. You find the area because we're way better at finding areas than just multiplying it, by the height or depth or whatever you want to call it in order to get the volume of that figure. So a few of them that we're most familiar with: rectangular solid or rectangular parallel piped, length times width times height. The surface area, right? There are 6 faces, all right, on a rectangular solid, right? Think of a die. All right, there are 6 faces on a standard 6-sided die. Circular cylinder. All right. Again, pi r squared times the height, base area times the height. And then the surface area is 2 pi r, right? That's the circumference times h, and 2 pi r squared, 2 circles, top and bottom, right? So surface area is just about the faces. Right circular cone, very similar to, it's 1/3 of a right circular cylinder. And then there's the surface area formula. Notice it kind of involves Pythagorean theorem in there. And then sphere. Okay, the sphere formula, logically, I could prove it, but take some higher level math. 4/3 pi r cubed. All right, again, it's a cubic. It is a volume. And then the surface area is 4 circles actually make up the surface area of a sphere. So let's look at some examples. All right, a punch bowl shaped like a hemisphere, aka half sphere, with a radius of 9 inches is full of punch. If we are filling cylindrical glasses that have diameter of 3 inches and a height of 3 inches, how many glasses can we fill? So let's start with the volume of the bowl. All right, it's a half sphere. That means the volume of a sphere is 4/3 pi r cubed. Half sphere means multiply that by half. We were told the radius is 9 inches. And then calculate away. 1,500 and change inches cubed. Again, now that we're in volume, cubic inches. Area, square inches. All right, volume of each glass. The glasses are right circular cones, a lot of glasses are approximately that shape. So pi r squared h. The diameter was told to be 3 inches, so be careful of this. That means the radius is actually 3/2 inches, right? Diameter is twice the radius, so the radius is half the diameter. And the height was told to us to be 3 inches as well. All right, so, all right, our volume of the glass is 21.2 cubic inches. And then how many glasses can we fill? Well, that's literally just the volume of the bowl divided by the volume of each glass. Which would give us 72, according to my calculation, 0.02 glasses. Now, be aware, I could round this off, and sometimes you can. I really recommend just leave it as the decimal. So often, unless you're dealing with actual counts, but this is like, all right, so often just better to be precise. Do the exact calculation. All right. Unless the question actually specifies round off to one thing or another. All right. I have an example. All sides are the same length. Find the volume and the surface area. So I have a hexagonal solid. All right. This is all sides are the same length. So if we're told this is 2 centimeters, that means it's 2 centimeters on every single side. Notice this did not say, all right, the angles are the same. So I have a right angle here. Okay, a couple things. This is not one of the shapes that we had previously, which means that we have to go back to our general concept of volume. Base area times the height. So let's find the area of this object. All right. The area, the shape is a hexagon. Since I have some right angles there, I don't have an equation for a hexagon, but a hexagon is simply just some triangles and some squares, or triangles and rectangles. So let's start with the triangle. We're told it's a right angle. I have sides 2 and 2. Well, using Pythagorean theorem, I can find, all right, the hypotenuse side, which is 2.83. Now that's helpful to me because since I identified my hexagon as triangles and rectangles, I know that this distance across is 2, but this height I did not know, but now I know it's 2.83. So, all right, the area of my hexagon, it is 2 triangles plus a rectangle. My triangles, by definition, I can use my A equals 1/2 area times the base. 1/2, 2 times 2. Base is 2, height is 2. For a rectangle, that's just length times width. We just found the 2.83 times 2. So the area of my hexagon will become 9.66 square centimeters. Once I have that, now in order to do volume, it's actually pretty simple. Because volume is just the base area times the height. The base area we found, 9.66. The height, oh look, it's told to us to be 4 centimeters. So the volume, all right, of my hexagonal solid, all right, is 38.63 cubic centimeters. Surface area, which we typically represent as SA. Surface area, again, if you are, it's not one of the formulas we had, it's not one of the shapes that we have the formula for. The basic concept of surface area is count all the sides. So let's start with the top side and the bottom side. Well, that's our hexagons. So the top side, I have two hexagons, both with areas of 9.66. Then all my other sides are these rectangles, right? I have these rectangles, and then I just have to count how many of them there are. Well, it's a hexagon, so I can't see them all, but there are 6, right? There are 6 rectangles that are 2 by 4 centimeters. And so surface area, all right, neither volume nor surface area are overly complicated as far as the calculations go, but it's just about keeping track of all the sides of the object. That's what we want to make sure we're focusing upon. All right, one last big concept here. So one little definition, bisect. And we've kind of already been doing this without really doing it in a couple of cases. Bisect means you're dividing something into 2 equal parts and creating a right angle. So when something is bisected, it's splitting it and forming a right angle. So for an example here, approximately how much material is needed to make the tent illustrated in the figure, height h and of the tent, okay, height h of the tent is 4 feet. The base B of the tent is 6 feet. Length L of tent is 8 feet. And then line H bisects side B. I want to find the volume of the object and the surface area of the object. Now, be aware, tents, we know tend to be hollow. All right, but we're going to pretend, all right, the tent is solid here. And I really just said tent so you know what shape in case you couldn't quite understand what the picture was representing here. All right, so this is a solid triangular prism. Okay, so volume. Once again, this is not a shape we're familiar with. But volume is still just base area times the height. So let's put our units on there. Okay, length L, 8 feet. All right, so that whole distance there is 8 feet. Base B, 6 feet. Notice, not drawn to scale. Height 8, H is 4 feet. All right, so, well, the base area is a triangle. 1/2 base times height, 6 times 4, times the overall height of the whole thing, which is 8 feet. Multiply that out, 96 feet cubed. So volume's pretty easy, all right, in this case. Surface area, and this is the one that we got to think about. Surface area, okay, let's start, all right, with the triangles, right? Triangle on the front, triangle on the back. Well, we actually already found actually, let's just say it, surface area. We have 2 triangles. So we have the triangle on the front, triangle on the back. Then, okay, there are 3 rectangles, but be aware, all these rectangles are not the same. The bottom rectangle, right, which is going to be 6 feet by 8 feet, that is not the same as the rectangles on the side, because that's this distance. And that distance we actually don't know, but we're going to be able to find out. We were told, right? Here's where the line H bisects side B. That's a right angle. And that splits the distance. So I'm going to be able to calculate that. My point is simply this. I have three rectangles there. They are not all the same. Two of them are the same, plus a different sized rectangle. Okay, so let's plug in the easy stuff. The triangles, right? 2 times my 1/2 base times height triangles that we already found. Plus, all right, two more complicated ones that we're going to deal with in just a minute. But the last one is actually pretty easy. We already said it. The bottom, all right, the bottom rectangle is literally 6 by 8. So there's actually not much to do on that one. So notice we already did like quite a bit, all right? We did the easy stuff and we busted through that actually pretty quick. Now let's go back, all right, to our triangles. This, all right, bisected. This side H, which is 4 feet, bisected. That means it cut this into 3 feet and 3 feet. It created right triangles. And specifically, I can break those down even further into individual right triangles, 3, 4, and oh, look, X. This, in case you're familiar, is the famous 3, 4, 5 right triangle, but let's just do Pythagorean to verify. Nine plus 16 equals x squared. Oh, look, 25 equals x squared, square root. X equals 5 feet. Like I said, it is the famous 3, 4, 5 right triangle. What that gives us, all right, back to our picture, that gives us our missing side here of 5 feet, all right, which means that now we can calculate the missing two rectangles because they are going to be 8 feet by 5 feet. Once we have all that, then we can calculate away. And when you do the calculations, you would see 152 feet squared. Again, surface area is square feet. But the big thing about this one is that when you have surface areas, all right, you just have to count the sides and think, are the sides the same or are they different? What are the shapes of the sides? Break it down piece by piece. All right. Another wonderful lecture completed. You have yourself a wonderful day.